Let's give a big hand to Professor Booth. Okay. And Professor got his bachelor degree in 1984 in Hamburg, and in 86 for his master degree in Göttingen. And later he got his PhD in 1989, yeah, in Max Planck. And then I think he went to Santa Barbara, a very beautiful California place for his postdoc. And then he returned back to Max Planck in 1990. And later he joined, I think, university in Mainz, yeah. And from 1995 and then 96, he became the associate professor. And also he, you've been in different places, right? And universities, Sigmund, and as a full professor, you must be very, very popular. Everybody wants you, yeah. So you visit different places, and finally in 2002, he returned back to Max Planck Institute as a director. So ever since he's conducted a very important research on surface science, especially for the biophysics and chemicals. So it's a joint discipline, yeah. So I think he used a lot of AFN technique to quantify still those surface phenomena. It's exactly what is the topic today, wetting, a multiscale phenomenon. And so I think we just give a very welcome in the finals week, Professor Booth. Okay.
I'd like to talk about wetting, a multiscale phenomenon. And let me start by thanking those people who did the actual work. I'm only the guy who motivated these people, which is Doris Vollner. She did quite a lot. Werner Steffen, Michael Kappel, and Rüdiger Berger. They are group leaders in my group, comparable to associate professor, I would say. Then there's Noemi Enchinas, Nangao, Sanyok Vog, Shudeng, Perikles Papadopoulos, who used to be PhD students or postdocs. Xu is now in Chengdu professor, Perikles is now back in Greece professor, and Sanyok is back in Korea professor, and so on. Then we have still as PhD students, currently Florian Geier and Frank Schellenberger. And Maria is also postdoc, she stays with us for quite a while. So they are the guys who did the work, who made the setup, did the experiments, and I was more or less coordinating and pushing them maybe from time to time. So let me start by, this is a general audience if I understand correctly. So let me start by reminding you of the relevance of wetting. It's such a normal phenomenon in our everyday life that people forget that there's some physical basis to it. Painting is a clear wetting phenomenon. You want to bring your paint to a surface and you want it to spread. Drops on glasses, I think, is the typical phenomena. On window screens, oil in the feathers of birds. Bringing out of herbicides, insecticides. In fact, research was much stimulated about bringing effectively insecticides and herbicides to plants. Printing, I already mentioned. This is quite a popular, let's say, phenomena, but it also shows that, we are used to that gravity and inertia is dominating. That's the dominating forces for insects, which are small, capillary forces, so wetting is much more important. So for this guy, gravity is he's not scared of falling down. But he's scared, or he really knows about capillary forces. He or she, I don't know. Here's a list of phenomena related to wetting, and some maybe not so much known, like flotation, textiles, and so dispersions. But flotation, most of our minerals are processed at some stage by flotation, so millions of tons. That's a clear wetting phenomena. So wetting is even there in technical applications where we don't expect it. So it's certainly relevant. Then as a scientist, one may ask the question, well, if this is important, maybe we know everything about it. So scientists want to quantitatively describe things, maybe we know everything about it. So let's look at a very simple, the most simple wetting situation you could imagine. You place a liquid drop on an ideal, flat, solid, inert, homogeneous, rigid surface. And this you do in a gas or in the vapor phase, so everything is settled, thermodynamic equilibrium. Can we quantitatively describe it? Is this well understood? There are certainly people who say, well, we don't understand this part. I would say, at least to a large degree, let's say the still challenges are not so enormous. If, however, we go to real liquids, to real solids, which means, let's say, this even water is not, I mean, a pure liquid. You always have hydroxyl, hydronium, you have salt. So if you go to mixtures, to solutions, to surfactants, or melts, dispersions, emulsions, whatever. If we talk about real solids, so it may be soft, they may be structured, they are certainly not perfectly homogeneous. There's almost no surface which is perfectly homogeneous. They may even react. So if we consider the fact that, if you place a water drop, for example, there's condensation, evaporation going on, particularly at the three-phase contact line. Then, or if you consider there may be dynamics, so drops may move, then our understanding is pretty poor. I mean, most of these phenomena are not quantitatively understood. Now, as a physicist, I would say, well, this is not so bad. If, let's say, this one is close to this one, then, you know, you treat it as a small deviation from the ideal situation. This, however, doesn't work. If, for instance, you take water and you add a little bit of surfactant, very tiny amount, which is difficult to avoid because there's always contamination. So if you have real water, then typically the dynamics, so the contact angle at the front and the rear, are very different and changes very much, not only a few percent, but maybe a factor of 10. So this is often not close to this one. That's why, I mean, this is a real challenge to describe real situations. So if the aim of, let's say, science is understanding and of engineering is control of wetting, then certainly most of it is not accomplished yet. So it's a big open field, I would say. So let's go back to the very fundamentals. So at least tell you what we understand. And this typically starts in all textbooks. So if you a liquid again on a solid, that people found out 100 years ago, there's lots of literature. If you place a specific liquid on a specific solid, try be as clean as possible, then they form a kind of characteristic contact angle, and that seemed to be almost always the same. So if you take, I don't know, polystyrene, you place a water drop, the contact angle is always around 70 degrees. So the idea came up, okay, there is one precise value for a contact angle, and then there is a very nice simple thermodynamic theory, which is named after Thomas Young, which tells that the contact angle here is given by this very simple equation. So this is the surface tension of the liquid, which is easy to measure. You can measure it precisely. This is the surface energy of the solid, of this interface here. This is the surface energy of the solid liquid. Looks nice, it's in every textbook, but it's more complicated than it looks like, because this part is individual, not measurable. You can measure the difference, but not individual values here. In addition, if you do the experiment, you will find that it's practically impossible to measure this thermodynamic contact angle. You will always find a range. In all practical applications, at least to my knowledge, you will find a range. So you will find that the contact angle you observe is between two limits. One is called the receding and one is called the advancing contact angle. If by any chance you exceed this contact angle here, then the liquid front starts to advance. If you get lower than this contact angle, then it starts to recede. But if you place a drop, you will be somewhere in the range, but there is not a specific value. And meanwhile, I would say it's difficult to say in science impossible, but I think it's impossible to measure equilibrium contact angle. So it must be a very special experiment. So you always find this range. So that's kind of a nuisance. We have a nice equation, but it doesn't really apply. And the range typically is like 20 degrees. It's not 1 degree, then I wouldn't worry. But I mean, you measure typical contact angles, glass, and then place a water drop, then it's between 40 and 70 degrees, for example. So not very precise. So it's a huge range. Now that's a nuisance. On the other hand, let's turn this around. It's essential that there is such a difference. Let's start by measuring those guys. You can measure the receding and the advancing contact angle, so those limits, by placing a drop on a surface and start to tilt. And at some point, the drop will roll down or slide down. And at that point, this is not 100% precise, but there is a receding contact angle at the rear and an advancing at the front. And the larger the difference between the two, the more resistance for the drop there is to slide. Let me turn the argument around. If these two angles are very close or almost similar, there is no resistance to slide. Now this would be nice for this case here, so the window screen would always be clear. No problem with drops on glasses. On the other hand, it would be impossible to paint, to code, do all those things. So the fact that there is a difference between these two values is essential to our life. And just for your experience, here is a surface which is now, let me pass this one, which has a very low difference in between advancing and receding contact angles. So the difference with water is maybe 2 degrees. I'll pass this around. I can also pass, let's take a fresh bottle of water. You may try placing a drop of water on top. It makes a difference, I mean, to feel how difficult it is to place water on top of such a surface. So let me start by passing it there. There's a big niche, okay. So play around with it. The point I'd like to make is that although this is always treated as, something like a nuisance, we can't use thermodynamic equilibrium, it's very important for our everyday life. I mean, coating, all these things would not be possible without having this difference here. So I think we should pay more attention to it and not just treat it as a nuisance. I must admit, even in our textbook, we treat it as a nuisance. So contact angle hysteresis, so the difference here is called contact angle hysteresis, is of fundamental importance. It's not only a nuisance, but it's inherent to our everyday life. And let me just briefly compare this to friction. I don't know how the physics courses here in Hong Kong are. I was pretty bored by the physics course in our school when we did these friction experiments. So we had a surface here, we had a block on top, and then we started pulling on the surface here until the block is moving. And then the teacher was very happy about the sliding and kinetic and static friction. So if you do this experiment, you increase the force more and more, and then at a certain threshold, the block starts moving. And then the force goes down because the sliding friction is slightly lower than the static friction. I mean, this is essential for if you have these electronic brake systems for cars, they use precisely this point. So it's something which is known. This was studied by people back 500 years. Amonton's law tells us, about this difference between the kinetic, so this part, and the static friction. So we thought, well, let's treat a drop, a liquid drop, like in this experiment. So Rüdiger Berger, Dominique Pilat, and several people set up this kind of thing. So you have a drop on a surface, and you keep it in place by a capillary. And then we pull on the surface so that the surface is moving underneath the drop. And by the deflection of the capillary, if there's a force acting on the capillary, then we can detect it. So we know what is the lateral, the friction force, basically, to slide a drop over the surface. Just for simplicity, we move the surface and keep the drop stable. So this is shown here. So this here is a drop. I think this is an ionic liquid. You can do this with many things, just to avoid evaporation. So we don't want that the drop evaporates while we do the experiment. So that's an ionic liquid. Here's the capillary. And this is the surface. Now let's see if I can get this to slide. Yeah, very good. Now this surface is moving in this direction here. And you can see how first the drop is stretched, but then there's a steady state. So that's the experiment. A very, very simple experiment, conceptually at least. And this is the result, and it very much looks like on solid friction, which I didn't expect. So the force increases until you reach a certain threshold. So here's force, here's time, threshold, and then it goes down and it goes to steady state. So it's pretty much like on solid friction, although the physical principles are very different. So it's very different. So you can only compare the phenomena. And we found that this is true for all kinds of combinations we used. So here we used, let me see, this is water on silicon nanofilaments, I guess. This is hexadecane on silicon, water on SU8 pillars, and so on, water on and so on. So every combination we used, you'll find this kind of, there's a peak initially and then there's a steady state. Peak, steady state, peak, steady state. That kind of complicates now again the situation, because until now everyone, including us, thought, you increase the force and then there's sliding and that's it. But even for drops, we obviously have to distinguish between kinetic and static friction. So distinguish between those two. One of the issues I'd like to point out today, although this is a subject, wetting is a subject which has been studied quite a bit, also superhydrophobicity, there are still very fundamental things to find out and to study. This is, to our surprise, one of those very fundamental things. Now I mentioned one aim of all this research is control wetting, and one aim of our research is definitely control wetting. I mean, like Shankar Wang, he wants to move drops. Also, one central issue is liquid repellency. I mean, making surfaces which like the liquid is easier than making surfaces which repel a liquid. So if we control liquid repellency, then we gain a lot. So one aim is how can you make surfaces which really repel liquids? And then if you start doing experiments, then you'll find out if you take water, for example, and you place it on a very hydrophobic surface, so hydrocarbons, fluorinated hydrocarbons, the contact angle is 120 degrees. You will not exceed it very much. So there's a limit, and there's a fundamental limit. However, of course, people observed already almost 100 years ago that there are leaves or wings of insects or feathers of birds. If you place a drop on top, the contact angle is much larger. So how is this? These surfaces are, if the contact angle exceeds a certain value, then we call them superhydrophobic. If you tilt the surface like the one I pass around, the drop is running off easily. So how does this work? And back in 1936, Robert Wenzel made the first experiment. He made, in fact, artificial superhydrophobic surfaces. He took paper and put some, how's it called, organic acids on top. And then he noticed that the contact angles go up to 170 degrees. So the liquid really balls up and runs off easily. So he made the first, at least to my knowledge in the literature, superhydrophobic surfaces. And he already noted that obviously roughness is important. His quantitative theory was not correct for this case, but then a few years later, Casey and Baxter, noted what the real effect is. The real effect is the following. Rather than having water in contact with a solid, and the apparent contact area is the same as the real one, they noted that there's probably some air underneath still. So the surface is so rough that at some points there is air underneath the liquid. And this is the effect of making superliquid repellent surfaces in stillness. You need to design a surface in a way that air gets kind of, I wouldn't say trapped, but air is stabilized by capillary forces underneath. So in reality, this drop is not in contact with a solid, but it's more in contact with air, even though, it's apparently on a solid surface. So you have to make a surface which leads to such a situation here. This has meanwhile been studied quite a bit. Let's get back to the lotus leaf. So in the lotus leaf, meanwhile, we can look with the electron microscope, and indeed, if you look at a lotus leaf, then it's typically very rough. So you can see all these micron protrusions, and obviously if you place a water drop, the water drop is sitting on top of these guys, and it's not getting in contact with this more substrate-like underneath. So this is how leaves get the superhydrophobicity. Now superhydrophobicity in research has been studied in many systems. We know many ways of making superhydrophobic surfaces meanwhile. One of the surfaces, which is the standard in particular for quantitative analysis, are these micropillars. And this is here taken from one of the papers of David Carré. So you make micropillars which have a flat top, defined size. You place a water drop on top, and then the water remains up here and doesn't touch the substrate, at least if you're careful. The effect, it's not pressure. So it's not that you pressurize the air underneath, but it's capillary. So the same effect which keeps a drop from falling down. So there's surface tension keeping this drop, pulling up, balancing gravity. So that the capillary force also prevents liquid from penetrating in between those things. So it looks more like here. So you have the water on top. There's a small curvature down here, and surface tension is stabilizing the situation so that the liquid doesn't penetrate into between the micropillars. It's not pressure. And as long as the contact angle here doesn't exceed the 120 degree on the flat surface, the situation is stable. So this is how superhydrophobicity works. And this is just one example to demonstrate one of the key features. Also, the adhesion towards the substrate is extremely low. So this is a water drop on a superhydrophobic surface. If you add a little bit of water, the guy starts vibrating, and you can see that it easily detaches from the substrate. So it's an extremely low adhesion. Let's finish this because so you see that it's very easy detaching from the surface. So that's really high liquid repellency, I would say. So the definition in all textbooks, again, and also in ours, is superhydrophobic surfaces, the apparent advancing contact angle should be above a certain threshold, typically 150 degree. In addition, you need a second part. This is not sufficient, you need a tilt angle. So if you start tilting, then these drops should roll off at a low tilt angle. Then depending on the volume, let's say 10 degree for 10 microliter drop is a good value. So that's the classical definition. I believe this is not a good definition, and I'll show for a specific reason. And therefore, I'd like to look at the following experiment. I'd like to look at what happens when you take a water drop on such a superhydrophobic surface and you move it, and to look at the front and at the rear. Meanwhile, all the theory assumes that, again, both is a deviation from, slight deviation from equilibrium. We believe it's a fundamentally different things which happens at the front and the rear. And therefore, we were looking at what happens at the moving drop. And we did so on a micropillared system because it's the standard system. So we fabricated these micropillars of hydrocarbon, fluorinated them. So typical spacing is here 10 microns, and we placed water drop on top. And then we used a confocal microscope to watch from below. So there's a confocal microscope. You send in light through the objective. This is, in our case, we don't even use fluorophores. We detect the reflected light. So light is reflected from the solid air and the liquid and the air-liquid interface. I'll show you in a second. We detect the light and we create an image of the sample. So let's start by looking at the front. So now we look at the front of a drop which is just about to start moving. And this is one of these images. So back here we have the glass substrate. These are the micropillars. It's not the real image. These we inserted artificially because for optical problems. But believe me, there's a micropillar. This is the water drop. And you hear this yellow part here is the reflected light. I mean, there's light coming from below. Partially it's reflected at the glass-air interface. Part is reflected at the air-water interface. And this is what we detect. Now you see that there are some holes in between, but that's just the artifact because there is the pillar underneath, and where there is a micropillar, I mean, optically it's just not visible. But believe me, the air-water interface continues in this line. I guess you can see the reflection. So you see the front of the liquid drop. And now, now I need to getting this to move. Here we are. So now this drop is about to start moving, and what you see is that it's basically the liquid air interface is just coming down. It's touching down like a caterpillar or like a wheel. So it's a non-spectacular process. There's no instability. It's basically just touching down. So here it's touching down on this pillar, then it's touching down on the next one, then it's touching down, and so on. So that looks a bit boring. In fact, it's not so boring, because most people, I mean, I was talking about an advancing contact angle. Now, question is, what is the advancing contact angle? I mean, it seems to be kind of 180 degree. There is no characteristic angle on the front. So everything, most of those values reported are due to the fact that it's very difficult to measure high contact angles. In reality, in most cases of these micropillars, the advancing contact angle is 180 degree. With a classical setup, you can't observe it, but if you look with the microscope, you'll find it's 180 degree. And we did many of these surfaces. So if you have flat top surfaces, advancing contact angle is always 180 degree. So the advancement is a touchdown, and if you want to define a contact angle, then it's, I mean, around 180 degree. In fact, if you look carefully in the literature, then you'll see that, I mean, these people here, Bartel, Shepard, back in the 50s, Chuck Ekstrand and McCarthy, they kind of mentioned this already. They mentioned that it's difficult to measure advancing contact angle. Probably it's a touchdown and advancing doesn't play a role. So they were very much looking in the future there. And we proved this. They also mentioned, at least in part, on the receding side, it's the same. This, however, is not the case. So let's look at the receding side now. So the drop is moving here. It's difficult to see, but there is a little bit of yellow stripe here. It's very thin because if you have a certain tilt, not much light is reflected back into the objective. This is why it's very faint. So again, here we have the glass, air, water. And now I try to start. Yeah. So if you can't see this yellow stripe now, you will see it once it has jumped to the next pillar. So we now start moving in this direction, and it's almost real time. Maybe there's a factor of 2 difference. And you can see that this is kind of moving up, then it jumps. Now it's moving up, so the angle is increasing, increasing and increasing. Until it's reached a certain critical value, and then it jumps to the next pillar. So that's a fundamentally different process. There is a clear instability, and second, there's a clearly defined angle. So let's keep this guy moving. And this we observed on again, different kinds of surfaces. So if you analyze these videos, then you'll find the angle is decreasing, decreasing, decreasing until it reaches a certain threshold. Then it jumps to the next pillar, decreasing, jump, decrease, jump, and so on. So in contrast to the front side, there is an apparent receding contact angle, and it is clearly defined and characteristic for your sample. And it's very different, so the advancing and receding is very different. So allow me one slide for the experts in the audience on superhydrophobicity, and I'll be fast. So drops recede via depinning at a defined receding contact angle. The advancing sign touches down. There is, if you want, a contact angle of 180 degrees, which means neither the advancing contact angle nor contact angle hysteresis are a good measure for superhydrophobicity. Both don't make sense. Instead, the receding contact angle is a very good measure for hydrophobicity. So I would recommend, and this is in line with the recommendation of Cohon back in 2013, using the receding contact angle. There is one nice fact. If you calculate the sliding angle, it's like a geometric factor, surface tension, width of the drop, mass, and gravity constant. Until, I mean, now you find in literature that's the difference between these two contact angles. If the advancing is 180 degrees, that becomes easier. Knowing the receding is sufficient to also know the sliding angle. So rather than having 2 parameters, we only need 1 to characterize superhydrophobicity. And then again, this Cassie-Baxter equation, which is always used, is not very useful. Because it describes a situation where the drop is not in equilibrium, so this is not useful. Okay, that was for the expert. Let's continue. Now, superhydrophobicity again is studied for 20 years extensively. Many people work on superhydrophobicity, so you would expect there's nothing new to discover. But let me just give you one simple example. Start again with a water drop on a solid surface. Now, task is let's make it liquid repellent. So you could start removing material underneath. So we entrap air, you could remove more material, you increase the contact angle. But at some point, this is not going to work anymore because the liquid will impale these structures and then you are lost. So then you lose all the nice properties. So the question arises, how do you make a good superliquid repellent surface? It's obvious, and we can image also the process. So this is a water drop on a micropillar array. It's stretched by a factor of 10 in the z direction. That's why it looks so strange. And the water is evaporating, the pressure is increasing, and at some point the water will impale the structure. So let's just let this run for a few seconds. So this is run faster because the drop's evaporating. You can see the impalement here. So it's one of these phenomena which you really want to avoid. But even this very simple, idea, not even experiment, thought experiments, it shows that to make good liquid repellent surfaces, there are at least 2 things you want to optimize. One is the high contact angle. The second is you want a high impalement pressure. Otherwise, the surface is useless. So there are always 2 things you need, at least. Now, knowing there are 2 things, how do you make a good superliquid repellent surface? Now, there are 1,000 ways of making these surfaces, but let's start with this geometry, which is the most simple one. Cylindrical micropillars, and let's assume the task is make a good superhydrophobic surface. You have a specific material, use this geometry. So which parameters do you choose for the pillar size, so pillar radius or diameter, and the spacing between pillars? That's not obvious, at least it wasn't obvious to me. So let's assume this is the structure here. You could, for instance, go keeping the surface area constant, but split those pillars, so split every one in 4, and continue splitting. That's one possible choice. As an engineer, you could also keep the number of pillars constant, but shrink them in size. And of course, you can make all kinds you can change all parameters, everything in between. So which one do you choose? So we did a calculation. We calculated receding. So, and we plot all parameters in this kind of coordinate system. Here's the radius of the cylinder, so increasing radius. And this is here like the pitch. So it's the spacing from the center of this one to the center of the next one. So we basically increase spacing. And then for geometric reasons, you can choose all parameters down here. This doesn't work because if the micropillar is so large, then the spacing to the next, the next one, if it touches the first one, then for geometric reason, that doesn't work. So, but this is all the parameters you can choose. Which one do you choose? So that's forbidden. Let's assume you want a contact angle receding above 150 degrees. Then a simple theory tells us that then you would like to be somewhere in this area here. So you want to be below this line. All combinations work. Let's in addition assume you want an impalement pressure which is above 3 kilopascal, and 3 kilopascal is not much. So you want a specific impalement pressure. So then you want to be above this line here. So the parameters you can choose are in this green kind of triangle. And even this very simple calculation, and there may be details wrong, but the scaling is right, shows you that obviously to achieve both high impalement pressure plus good wetting conditions, you need to go to small structures. So there's no combination above 10 microns which works. The smaller you go, the more flexibility you have. So super hydrophobic structures, and I think this is also true for oil repellent surfaces, should be as small as possible, which is in line again with one statement of Chuck Ekstrand back in 2006. This is now quantitative. So that's a very simple message. Huh? Let's look back at the lotus leaf, because the lotus leaf obviously had these huge micron structures, 10 micron, 20 micron structures. So obviously it doesn't seem to follow this rule. So we took one lotus leaf and had a look ourselves. So here again is the microstructure. So this is 20 microns. That's a bit large for being a stable, robust, superhydrophobic surface. However, if you zoom in, then you indeed find that there are nanostructures on top. So they have a microstructure, but on top they have this hierarchical nanostructure. And this nanostructure is the one which prevents impalement. So they indeed follow the rule, go as small as possible. Then you may ask, why the heck does this lotus leaf then have these microstructures? These ones would be sufficient for contact angle and for impalement. Most likely for mechanical robustness. These ones here get just mechanically prevent things from touching the surface and destroying it. So this adds mechanical robustness. So at the end, what you really need to do, and this is the challenge, and this is still a challenge, you need to combine high contact angle, high impalement pressure, and mechanical robustness. For any application I know, you need a combination of those three, and this is difficult to achieve for fundamental reasons, not just because we are too stupid. That may also be the case. But there are fundamental reasons. You can achieve one of the three. You can partially achieve two, but achieving three, you need complicated structures, hierarchical and small ones. And this is still a challenge. Now let's go one step further. Water is nice, but if you let's talk about oily substances. Oil superhydrophobicity is lost if you go to oils, or if you go to surfactants or protein solutions. So if you want to go to useful liquids, or to many practical liquids, then superhydrophobicity sometimes fails. So how do you make oil repellent surfaces? And we need this, and you know that superhydrophobic structures like, feathers of birds are superhydrophobic, but they fail if they get in contact with oil. Everyone knows this, which is deadly for birds because then they lose the heat protection and they can't fly anymore, so that's a clear, they will die. No way out. So what's the difference between water and oil? Simple difference with respect to wetting. As I said, water can form contact angles significantly above 90 degrees. To my knowledge, there's no oil which forms a contact angle above 90 degrees on a flat surface. So it's always smaller because the surface tension is lower. So water you can use, for instance, these micropillars. This is not going to work with oil. With oil, you need these overhanging structures. So you need something like a sphere on top of a stick or a tabletop. And this was first realized by, at least to my knowledge, by Stefan Herminghaus theoretically, and then by Bob Cohn and Gareth McKinley at MIT practically. So you need overhanging structures, and this in the nanometer regime if possible. And these are the first practical solutions. So they made these tabletop structures by lithography, and you could really place an oil drop on top, and it had a huge contact angle. Electrospun fibers. Then there's a very good solution by Stefan Seeger group in Zurich. They made these nanofilaments. The liquid is then hanging underneath these nanofilaments. We made our suit templated surfaces. Meanwhile, there is this Korean group which even has overhang plus a second two-tier overhanging structures. And then there's liquid flame spray. Meanwhile, I mean, right now, at least our group, we are using those three types of structures because they combine nicely some mechanical robustness, very good wetting properties, and easy to make. These lithographic surfaces are, of course, nice for fundamental things, but useless, of course. So we use those ones. And then there are some applications. But before looking at applications, let me demonstrate that we can really make super amphiphobic surfaces. Now this is getting a bit more messy. Let's pour this out. So this is one commercial ketchup which I bought somewhere, I don't know. I forgot where. This is again one of those textiles we use, which is coated with these nanofilaments I just showed you. Now I'm not sure if this is going to work. I passed one around that this is super hydrophobic. I mean, you already realized that's easy to achieve. However, this is also oil repellent. And to demonstrate this, this is not only oil, but ketchup, typically ketchup repellent. So if I place a little bit of the stuff on top, oops. And this is a commercial ketchup. I just lost the etiquette, but it's a very standard commercial stuff. You can see that you can roll this guy around in the surface, and it detaches 100%. I'll pass this around in a minute. The advantage of this material is you can even, it's also mechanically robust. So if you step on this, it's typically still super oil repellent. And as I said, I'm going to pass this around, but be careful. Ketchup is really nasty. I mean, so don't complain afterwards if you waste your... So that this is still rolling around. I hope I don't lose this and let this fall on the floor, but it's still rolling around. I'll pass this on. The only thing, so let's start here, but be careful. I mean, ketchup is quite in use. The only thing you should not be doing is take this sheet and turn it over and press. Because if you press, then the ketchup is kind of squeezed in all these small cavities inside, and then superhydrophobicity is lost again. But as long as it is lying loosely on top, it's typically working. And ketchup is difficult because due to its mechanical resistance, it's difficult for all these applications. We also played around with, in fact, Volker's blood. That's a cooperation with Volker Meilen, a doctor. He donated blood, and we coated a metal basket with the super amphiphobic layer. And when you pour the blood and let it stand for 24 hours at 37 degrees, you could just take it, pour it out, and nothing is left behind, which is pretty remarkable for human blood. We played around precisely with those guys for membranes to capture CO2 in an ethanolamine solution. That's one possible solution of recapturing CO2, and at one point we need to be able to recapture CO2, otherwise, I mean, the Earth is going to increase in temperature all the time. I'm not sure if this is the solution, but engineers told me that using membranes is more efficient than the way they do it currently. So we made some membranes. Let me see. We coated one textile, and indeed this ethanolamine solution is repelled. And then we measured the efficiency of these membranes and compared them to standard commercial membranes, and the super oleophobic membrane is more efficient than the standard ones. I should say, however, this is not a fair comparison because the geometry is completely different. It's just, let's say, promising, because the first attempt, even using one of those, textiles, which is not optimized at all, even has a higher efficiency than all those existing membranes, which is good. It's a good start, let's put it this way. Oops. Let me show you one last application of these samples, which is making supraparticles. If liquid balls up, then one could do the following experiment. Take a suspension, which contains small particles dispersed. Let it evaporate, and then at the end you should get a supraparticle, so a large particle consisting of small ones, which you then may use, for example, for catalysis. So we tried our surfaces, but and then you realize again there were people who had the idea before and used superhydrophobic surfaces. Orlin Welles' group was the first one. Here they have a supraparticle, which is typically a millimeter in size, consisting of smaller particles. And then you see this opalescent shining. If you add gold particles, they become optically interesting. Michael Grazielski's group, they could make different shapes, this is not, here. In Detlef Lohse's group, they analyzed these particles. You can see these crystalline areas of particles on surfaces. However, I mean, this is nice for studying fundamental things, but it's difficult to remove those supraparticles because they still stick pretty tightly to the substrate. So our idea was that with our super amphiphobic surfaces, we could easily remove particles and use this to produce in a very in an easy or defined way complex supraparticles. And just to give you one example, so this is a drop which contains titanium dioxide nanoparticles of 21 nanometer size in water. We let the water evaporate, so at the end, then after 15 minutes, we are left with a supraparticle, this is, battery seems out, which looks like here. So this is now a particle a few hundred microns in size. It's very porous in this particular case, which is nice because we want to use it for photocatalysis. And this is all titanium dioxide. The particles, the nanoparticles are so small that they basically sinter together. So it's mechanically very stable. And then we use it for, I mean, just to show the proof of principle for photocatalysis. So here's a Teflon tube, and we filled it with these supraparticles. It's closed at the back and at the front by rough filters. And then we had a reactant running through. In our case, we used a rhodamine solution. Rhodamine just because it's simple to see then if there's a photoreaction. So here we have the rhodamine solution running through the tube. There's some UV light, and at the end you can see it's completely transparent liquid. So obviously the photocatalysis of this titanium dioxide worked. So that's one way of using those supraparticles. Doing these experiments, the idea came up it should be nice to combine superhydrophobicity with photocatalysis. So use photocatalytic active materials and with a high contact angle. That turned out to be difficult. And the reason, so the idea is again, for example, now take water drop or liquid, place it on, for example, titanium dioxide. Titanium dioxide is a very good photocatalyst. And this can be achieved. I mean, make a pillared structure, coat this with a silane or some acid, so that's not a problem. So superhydrophobicity is not a problem. And then use this for photocatalysis. So again, the idea is in the titanium dioxide acts like a semiconductor. If you shine UV light, you create these electron hole pairs, and then they create in turn radicals where you can do all kinds of chemical reactions. So titanium dioxide is used a lot, and not only titanium dioxide, zinc, tin, silver oxide. So there's a number of metal oxide photocatalysts. So it would be very nice to combine this with superhydrophobicity. However, this never works because if you shine UV light to this situation, this is what happens. Contact angle goes down and the liquid spreads. Here's a movie. So this is a water drop on top of a, superhydrophobic titanium dioxide surface made superhydrophobic by this acid. If you shine UV light, the liquid just spreads and the drop disappears. And the reason is again kind of fundamental. If you attach something hydrophobic to the surface to make this hydrophobic, there's a linking group. And of course, if this is photocatalytically active, the first thing it does is kill this linking group, and then all the hydrophobic surface goes down. It's a nice way of cleaning surfaces, but in our case, we want a stable hydrophobic surface. So and we always wanted this for years. And then San-Yuk had this brilliant idea of testing something very simple. He put this titanium dioxide or metal oxide photocatalyst in a melt or in a solution of PDMS, polydimethylsiloxane, silicon oil basically. Some UV light. And then he obtained surfaces which are hydrophobic and stable, UV stable. What probably happens is that there's a covalent link between the metal by an oxide towards the silicon. And then you get these direct silicone bonds towards the PDMS. We are not sure of this. There's some XPS data supporting this idea, But we don't know the structure, but we know it's UV stable for a long time, and you get the typical contact angle of PDMS. I should say probably it's somehow similar. McCarthy and Stephen Hart observed that if you take also silicon oxide, aluminum oxide, place PDMS on top and you heat, then you get also a covalent bond between the PDMS and the oxide. So heating probably does the same as UV. UV is just simpler. I mean, you just put this in the bath, shine some UV, and in a few minutes you are done. So it's very fast. To demonstrate that this works, so here's a titanium dioxide, zinc, a silver oxide surface, and you can all make them hydrophobic. You had contact angles significantly above 100 degrees, UV stable, UV doesn't harm it. You can make super hydrophobic surfaces, which again are UV stable. So here's mesoporous titanium, zinc oxide, titanium micropillars, all super hydrophobic and stable in UV. Furthermore, and that was really surprising, they are still photocatalytically active. So here we place a water drop on top of a flat titanium dioxide coated with this PDMS. And there's some Nile red immersed. So that's why you see this red color here. Place a water drop, which we image by confocal microscopy. And then you will find there's a contact angle of 103 degrees, which is typical for the system. If you shine UV, the Nile red is gone because the substrate is photocatalytically active. But the contact angle remains the same, which means the PDMS is still there. So it's stable hydrophobic and photocatalytically active, which is a nice combination. You can do this also with oleic acid. So you take this surface, you add oleic acid, the contact angle goes down because the acid goes to the surface. You shine UV, the oleic acid is destroyed, and you can do this repeatedly. So you can play UV, add acid, shine light, and so on. So it's all pretty stable. One of the issues which always comes up in any surface basically you make is biofouling or biocompatibility. It's something you basically cannot avoid. So one standard test is you place your sample in a solution of E. coli and you look how fast E. coli is growing. And we did this with bare titanium, with a PDMS-coated titanium in dark and under illumination. I mean, that would be the standard test. And here's the result. So we look at movements of E. coli and they are stained. So the green ones are live E. coli, and there are some red ones down here, which are dead E. coli. And you can see that in the dark on bare titanium dioxide, I mean, they feel pretty happy. There are many alive, they don't move, they just settle, and eventually they form a thick biofilm. If you shine UV light, even on the bare titanium dioxide, you get this photocatalysis, which the bacteria don't really like. So the number is reduced, and the number of dead cells also increases. So titanium dioxide in light is not liked by bacteria. If now you take the PDMS-coated surface, you'll see first that from here to here, the number of bacteria is reduced, and they are much more flexible. So they're not so much prone to form biofilms. And then if you combine both effects, PDMS plus UV light, then you'll see that the bacterial number is again decreased and they become highly mobile. So I don't say this is anti-biofouling, but it's certainly not as well biocompatible, or bacteria really prefer pure titanium dioxide rather than the PDMS-coated surface. Last issue, self-cleaning. I mean, the superhydrophobic surface became well known because of the self-cleaning effect. You know, you take your surface, you put some dust on top, and then rain is washing the dust away. That was called the lotus effect. However, this worked only as long as there's no oil. So here we added some rhodamine B as an oily substance, and you can see this contamination here in the superhydrophobic surface. Here's some chalk, which we colored so you can see the dust, and then this is a superhydrophobic surface. Now I have to, now we first use water. Here. So we first use water to get rid of the dust. And you can see that, I mean, this works nicely. You can take, did this stop? Why do you stop? Let's go back. Let's try again. There we are. touch you, I don't touch you. So that the water is kind of rinsing the dust away, which is, I mean, what you expect of a nice superhydrophobic surface. There's the lotus effect that seems to be working, but you cannot get rid of the rhodamine because it's in between all those pillars and the roughness. So that's pretty well stuck in the surface. So there's no way of getting rid of this rhodamine. So we can get from here, clean the dust away to here. But then on these surfaces here now, coated with a PDMS, you just need some UV light, and then you get rid of also the rhodamine by photocatalytic activity. So in this case, if you place this on the roof, there's even hope that you get rid of oils due to the sunlight, and you get rid of dust due to rain, if it rains. So that adds another aspect to self-cleaning. So let me summarize or conclude. The aim of, what Shanghai and other people and we are doing when we study wetting is to understand, quantitatively understand wetting and control wetting. I'm certainly in favor that contact angle hysteresis should be taken more seriously than it has been done before because it adds friction. The challenge in superliquid repellency is not to make only liquid repellent surfaces, but combine at least those three properties: mechanical strength, high impingement pressure, and high contact angle. Challenges in the future are also multifunctional surfaces, so that you combine superliquid repellency with an additional function: self-cleaning, anti-biofouling, photocatalysis, whatever. Transport, like in Shanghai's group. And then I presented one way of making superhydrophobic or hydrophobic, photocatalytically active metal oxides. With this, I'd like to finish. Thank again those people who did the actual work or provided the framework in which one could work. Also thank those institutions which gave the money, but beside the Max Planck Society is mainly the German Research Society and the European Research Council. And I'd like to thank you for your attention. Thanks.
Excellent talk. So now we have a Q&A sections. Any questions from the audience?
Okay, thank you, Professor Brott. I saw you introduce some research about liquid-solid friction. So, is it same to the conventional solid-solid friction?
No, it's certainly not the same. The first difference, or the main difference in solids, if you have two solids, let's say that one of the fundamental laws in solid friction is that the friction depends mainly on the weight, not on the apparent contact area. The reason being that surfaces are always rough and the actual contact area is very small as compared to the apparent one. That's not the case for liquid. I mean, if you place a liquid on a flat surface, the apparent contact area is the same as the liquid one. However, if you treat this phenomenologically, then it appears that we have to discriminate between the static and the kinetic part, which has not been done in the literature so far and which complicates things again. It even makes fundamental questions difficult because now you may ask, what in fact is the receding and advancing contact angle? Does it relate to the peak or does it relate to the static movement? So it's not the same, but some phenomena are the same, I would say. Let's put it this way.
Okay. So as I know, the solid friction maybe have two different regimes: static friction or kinetic friction. So the liquid solid friction also has these two regimes. Yep. So this kind is same.
That's the same, yes.
Okay, thank you.
Even the order of magnitude seems to be the same.
Okay, thank you.
Yeah.
Any other questions? Yes.
Hi, Professor Ra. Actually, my question is also about.
Sorry.
It's also about the friction. As we all know, when we are thinking about the factors that may thwart the droplet motion, we usually, first of all, we use contact angle hysteresis. Then maybe also the viscosity between the liquid and the solid. So I wonder which factor will dominate the friction at different stages.
Yeah, that's a difficult questions like on solids. That's also a difficult question. Depends on, I mean, on the shape of the drop and on the velocity. So if a drop is sliding very fast, I don't know, fast means 10 centimeters per second, a meter per second, then viscosity certainly plays a significant role. If, let's say, a drop slides with a millimeter per second, viscosity typically, definitely not for water, viscous dissipation plays not such a significant role. So the velocity regime plays a role, always taking also the viscosity of the liquid in consideration. Second, it depends on the surface itself. Let's assume you have a very smooth surface and a smooth gliding process as compared to one which is very heterogeneous, or as in our case, a superhydrophobic surface. On a superhydrophobic surface, you always form these small bridges between pillars and the liquid. You stretch these bridges and then they break and you lose all the energy required to stretch a bridge. So there is lots of energy dissipation, in particular at low velocity, due to making small capillary bridges which you lose. On smooth surfaces also the adsorption-desorption processes take place. So you have different processes in different geometries and for different surfaces. That's why a universal answer is impossible. It's not only possible, it's not only because I don't know it, because I'm too stupid, but there is no universal answer. There are different factors which contribute depending on the conditions.
Okay, thank you very much.
I think Thomas will go first.
So just for my curiosity, I would like to ask this, so since there is some kind of photocatalytic particles sticking on this kind of hydrophobic surface, so is it possible to stick some kind of molecule machines on those kinds of hydrophobic particles?
In principle, you can dissolve everything. After evaporating the liquid, it will be somewhere. So in principle, you are free to do whatever you like. We just need to show what these molecular machines are supposed to do. There are, however, limits which I didn't, or let's say problems which occur which you find only when you do these experiments. For example, I mean, for photocatalysis, our particles are not useful because they should have big channels. Otherwise, I mean, they're not, for hydrodynamics, it's stupid. So they should have big channels. So we inserted polymer particles, burned the polymer away. But this didn't work because obviously the large polymer particles assembled in the inside. We didn't know why. Now there is a theory telling us why. So if you start making more complex particles, you will encounter new problems and new challenges, but I think this is one way to go. I mean, include more complex function like machines or more chemistry. Yeah, more step chemistry, for example. Yeah, I agree.
From your presentation, I discovered that I'm more interested in the multiscale phenomenon, and that's why I'm here.
Yeah.
I would love to know why, in your presentation so far, you only mention changes in size.
Yep.
For example, the protrusion becomes smaller. I'm interested, how does the changes in the micromechanical properties affect wetting? For example, instead of changing this, making the protrusion smaller, how does the changes in the scale affect these properties?
Yep.
And also, how does temperature affect the efficiency of this system? Temperature change maybe in cold condition or in tropical condition.
Mm-hmm. So let's start the last one first. Temperature is kind of predictable. I mean, you could, for hydrophobicity, the surface tension goes down, vapor pressure goes up, viscosity decreases. These are things which you could predict basically. Some superhydrophobic surfaces break down at high temperature because, I mean, the surface tension comes down, so that's predictable, nothing special. Multiscaling is a fundamental phenomena in wetting. Not only in making these features small, but and the example is precisely, if you look at any dynamics, so any liquid moving, then you'll see that, let's say this is a drop which is moving in this direction, then you see a certain flow pattern in the middle, and if you go more to the rim, then you'll see that to get this guy moving, you have much higher shear rates. So as soon as dynamic comes into play, phenomena close to the contact line, so on the very small scale, start dominating. This is one of the main reasons why I call this a multiscale phenomena. although, I mean, this is only a tiny, tiny volume, since the shear rates at the very end are so high, the whole dynamic process is often dominated by what happens here. This is classical hydrodynamics is helpful, but it doesn't tell you how, let's say, a liquid flows as soon as three-phase contacts come into play. That's why I call this multi-scale phenomena. And there's no way around it. I mean, people still struggle with it. So as soon as dynamic comes into play, it's really multi-scale. You can't help. I mean, that's how it is.
I have a question. It's about those array, like a micro pillar or sometimes narrow pillars.
Mm-hmm.
And when we do the narrow pillar by, for example, like bauxite beam, the
Mm-hmm.
top surface is not flat.
Mm-hmm.
And also sometimes it's a flat original, but when you do the erosion or corrosion or your biocorrosion, the top surface become rounded and
Mm-hmm.
it's not the original.
Mm-hmm.
So, and also sometimes do the polymer and metals, not necessarily ceramics. So the surface conditions change as a bunch of time.
So it's not so bad in superhydrophobicity as long as you have, let's say, some vertical walls.
Okay.
It's not so bad that on top you may have something else. It may change the receding apparent contact angle a bit because at some point you need to detach on the rear side, you need to detach the liquid from it.
Yeah.
And there the shape plays some role.
Yeah.
But it's not so sensitive, I would say. Unless you go to oils, then you need this overhang. And you need the overhanging structure. Of course, if you round this up, that it's not an overhang anymore, you are lost. So for water, I would say it's not so severe if it comes to oily substances or surfactant solutions, proteins, and so on. Then you really need to look at the precise shape at the end of your protrusions. Yeah.
Yes.
Yeah. Today you are talking about the topic of your talk is about weighting. However, you are focusing on the hydrophobicity, which is by weighting. Okay. How about the other extreme? I mean, it's a hydro. It's more very hydrophilic. How do I say that? Hydrophilic, right?
Mm-hmm.
If the contact angle is approaching zero.
Mm-hmm. I mean, this is also an interesting point, for example, for making. So anti-fogging is one issue which people have. Let's say you don't want to look at the window, which is full of tiny drops. Then you prefer having it very hydrophilic so that drops don't form drops, but flat surface and roll down. Typically, you can achieve this with a clean inorganic surface and make it a little bit rough. So as long as the contact angle is below 90 degrees and you roughen it, it becomes even smaller. This is why for many applications making something hydrophilic is not so difficult. Sometimes it is, of course, if there's all hydrocarbons around, then you may get into trouble, but normally it's not so difficult.
But from heat transfer point of view, sometimes hydrophilic is better than hydrophobic.
Yep, and there's a huge effort to make heat transfer more efficient, but in fact more by a combination, so that you have drop-wise condensation, but the drops don't grow too large, but roll off more easily. So there should be some hydrophilic patches where they nucleate grow, but only to a certain size, and then they should roll off. So that becomes then more challenging. Yeah.
I have a question about the contact angle hysteresis.
Mm-hmm.
It's about the receding contact angle. When the droplet moves to the right and then the receding angle increase,
Mm-hmm.
then it reached a critical angle.
Mm-hmm.
I'm interested about the critical receding angle.
Mm-hmm.
I want to know what's the reason is about cause the critical receding angle.
Mm-hmm.
Such as because the critical angle is very important to the contain the hysteresis.
Yeah. I mean, it's in fact the receding angle is the important one for sliding drops on all kinds of repellent surfaces. I mean, first is you want to have as little contact line as possible. So make small pillars and widely spaced. The smaller and the more widely spaced, the higher is the receding contact angle. The only problem is at some point, of course, you get impalement. So make the pillars as small and as widely spaced as possible, but narrow enough to prevent impalement. So that's a trade-off, and there's no way around it. Small is always better. So let's say if you start with pillars, let's say 10 microns apart, 1 micron in size, that's good. But if you have 100 nanometer, 1 micron spacing is better. If you could go to 10 nanometer, 100 nanometer spacing would even be better. But that's probably not possible.
Thanks.
Any other question? No? Okay, please.
Thank you for your inspiring talk. I have a question about vocal imaging. I'm wondering how you imagine such a beautiful phenomenon. I don't really know how to observe it. Thank you very much.
Yeah, what looks easy is in fact the development of Pericles, Frank, so 3 to 4 people over the years of, let's say, optimizing the confocal microscope for these questions. Also, I mean, the movie I showed you, the movie was still taken, we always wanted to see moving drops, was still taken by tilting the whole table until the drop starts sliding. Meanwhile, we use a micropipette and shift the micropipette to move a drop. Or Shudeng is also doing it this way. But that's, I mean, there are many small things. You need to find the right dye, many small things. So there's not a trivial answer. And there's also this optical distraction which you have to take into. This is why these green squares I showed you, that's not the original micropillar. I mean, no, you can't see them. We just inserted them. I mean, in reality, in the figure you get, there's some obscure optical whatever. We know it's there, and the rest is an artifact, and we know why and how, but we cut it out in these images. I mean, the yellow part is okay, and you also have to play around with fluorophores. So we use in these images we don't use fluorophores, but often we add a fluorophore to see the bulk liquid also.
Please.
Yeah, thanks for the talk. I want to ask how about the chemical stability of the polymer brush on the titanium oxide under long-time UV illumination?
I mean, we played around for a week or so. That worked.
I also noticed you have very low, this kind of 5 microwatts.
Yeah, he also used higher ones.
Yeah,
so he used, I remember one which is 50 milliwatt per square centimeter over a week. That seemed to work.
So can you comment why it's so stable?
I don't know. I don't know. In fact, I told him, this experiment will not work. If you want to waste the day, fine with me. He spent the day and it was not wasted.
So let's imagine if we have the titanium nano-oxide, nanoparticles inside some polymers with similar chemical environment, let's say in the PMS polymers, peptide gels. So do they still have the similar effect of the both stability and the photocatalytic effect?
You mean with the PDMS coating or without?
So in your case, you have the polymer brush on the surface. Let's say if you have the polymer gel embedded with nanoparticles.
That still works. And yeah.
Have you tried that?
Yeah, what we tried is we coated titanium nanoparticles with PDMS, and we suspended them, we dispersed them in toluene.
Yeah. So that's the particle. Let's say if we have the gel kind of thicker films blended with nanoparticle.
Yeah. Now we have to distinguish. We are doing, I can't answer this now. We are doing experiments right now where we try to shift or increase the thickness of the PDMS layer. Because the first, I mean, if the titanium dioxide is photocatalytically active, one may question if there's 10 nanometer in between, how can there be photocatalysis? The question is whether the reactants diffuse through the PDMS or not. So if you make a gel with particles inside, if the reactants can move in the PDMS, I would guess, it's only a guess, I would guess it's still photocatalytically active, but I guess once you have exceeded a certain thickness and the reactant is not able to dissolve or at least partially go into BDMS, then you lose the photocatalytic activity.
So there might be an effective distance for the diffusion of the radicals, right? Also the okay.
Yep, yep. Yeah. That's what we try finding out now.
Yeah, thanks. Yeah.
Oh, over there.
Hi,
sorry, I have too many questions.
Fine with me.
I'm very interested in the friction, so could you specifically demonstrate how to measure the friction force?
I mean, there are two ways. One is really the micropipette. It's as simple as, I mean, basically you can do this on your own. Put a drop on a surface, take, let's say, a pen or a small stick, and you slide it, and you measure the force required. We did this with an optical beam, but it's really simple. Now Alexander is making a setup. You can buy force sensors which are pretty sensitive, which use capacitive coupling, and we stick this force sensor into the drop and then start moving a surface. But it's really not difficult. I mean, this is a micropipette which I think we drew this ourselves. So you can buy these glass micropipettes, use a patch clamp puller to make them even thinner. But this is very simple mechanics. I mean, Dominic took 2 days to build the first setup, and then a year to make it routinely working. But it's very simple. Or you could also use a hair. Maybe a hair is better because it's thinner. I mean, I can't do this anymore, but you could take a hair and move a drop. Then you will see that the drop will bend the hair, and from the bending of the hair, you can, in principle, calculate the force required to drag a drop.
Thanks again.
Thank you.